In the next example, this example, we want to look at another geometric problem. The new feature here, well, it's not a new feature because some of the way it's worded uh, doesn't really allow to exploit what I want, but it gives a hint of something that may happen. So the problem here asks you to find the angle theta that maximizes the area of the isosceles triangle whose legs have length L, using the fact that the area of such triangle is given by A is equal to L squared over 2 times sine theta. Okay, so what is the point here that I want to make? The way the problem is worded here in this example is such that they actually giving you everything. The most convenient way of presenting the problem, so you just need to look at they already giving you the objective function, and you just need to do whatever we learned. It's pretty obvious what the interval is going to be for theta and everything. You don't even need to think about the constraint of the size of the legs here, because it's already incorporated in the formula for the area. So sometimes, I told you that one of the crucial steps in solving these kinds of problems is to make the right choice for the variables you are going to be using. So for some of you, if the problem wasn't worded, if it weren't worded like this, so if you were given instead just an isosceles triangle, and you were asked to find the optimal dimensions so as to maximize the area, you may think naturally of introducing a new variable to be the other side of the triangle. Well, in fact, obtaining once you write the area in terms of this variable, you also need to introduce h, right? And you have to find a relationship between the two, which is that h squared plus x squared over 4 will have to be equal to L squared. This is very natural, and then you have to take the square root of to write h in terms of x, you will need to take the square root of this quantity here, and everything will be a mess. So whenever you have to take derivatives, everything will be unnecessarily complicated because of your choice of variables, which is not the fortunate one. So whenever you may be given other problems involving triangles, and I think in most of them, say if you have an inscribed triangle, a triangle inscribed inside a circle, inscribed on a circle, I'm sorry, then think of the most natural choice of variables as being angles, not sides. So let's forget about this then. So what is this thing? And the other point is exactly the one about the right choice. I was trying to tell you, you need to introduce, if you introduce x, you need to introduce the height. But if instead you think of the angle theta, so now we're gonna go ahead and write the solution. So if you instead think of the angle theta, even if you don't remember this formula for the area, it is very easy to derive. It will be beneficial if you spend some time trying to remember this formula instead of going ahead with the brute forcing your way through the problem by using x and h. This will pay off, I guarantee you. So even if you don't remember, so if you call this side x and the height h again, this angle here is theta over 2. Okay, so that's what the problem tells us. So since the triangle is isosceles, this is actually also x over 2, and from here to here we also have x over 2. So what do we know then? That the area is equal to h times x over 2. Okay, but what is h? Well, let's look at this triangle. The triangle. Let me look at. Let's look at this triangle here. From this triangle, we can see that h over L is the cosine of theta over 2, while x over 2 divided by L is the sine of theta over 2. And from these two relations, we can multiply them to obtain h times x over 2 is equal to L times cosine of theta over 2 times L times sine of theta over 2. And then, well, this implies that the area, because h times x over 2 is the area is equal to L squared times cosine of theta over 2 times sine of theta over 2. But the formula for the area here gives you a in terms of L. Well, L squared over 2 is already there, so we already have that term. But what about sine theta? Well, here we just need to remember that the sine of 2 alpha is equal to the sine of alpha, no, 2 times the sine of alpha times the cosine of alpha. If we apply this to alpha equal theta over 2, we obtain that the sine of the sine of theta 2 times theta over 2 is going to be equal to 2 sine of theta over 2 times cosine of theta over 2. So in all these implies that sine of theta sine of theta over 2 is the same as sine of theta over 2 times the cosine of theta over 2. So going back to this formula, then we obtain that this is L squared over 2 times the sine of theta, which is what was given to us at the beginning. Okay, so then after this discussion, we go back to the solution. And here we already have the objective function. So remember, I mean, the only point I was trying to make now is that in problems involving triangles, angles may be more natural choices for the variables. So the objective function is a of theta equals L squared over 2 times sine theta. And here, so theta is in the range 0, and pi. So it's a closed interval situation. So we look at the endpoints, and we see that a at 0 is the same as a at pi, and it's equal to 0, because sine of 0 is the same as a at pi is equal to 0. Now we look for critical points, and a prime of theta is equal to L squared over 2 times cosine theta. And if we set this equal to 0, then that implies that theta is equal to pi over 2. Pi over 2 is the only value between 0 and pi for which cosine is equal to 0. So this is the picture then that we have for the optimal triangle LL, and this is a right angle. So this is maximized then for theta equals pi over 2. And what is the area there? Well, a of pi over 2 is equal to L squared over 2 times the sine of pi over 2, which is equal to L squared. What happened there? L squared over 2 times 1, or L squared over 2. We see that we can compute actually directly in the case of straight angle the area, because if you flip this triangle here, the height is L and the base is L as well. So you have L times L over 2, which is L squared over 2. Another thing to notice is in many of the problems, if this is a multiple choice problem, whenever you're given a formula like this, it's immediate. It should be apparent to you. I mean, even if you don't remember how to solve these problems, since we're looking at a range where sine is positive, so this is the range in which we're looking. So this is the possible range of values of theta. You know already that the maximum value of sine is 1, and it's achieved inside this interval at pi over 2. So that should be the maximum. L squared over 2 is just a constant, so it doesn't really matter. Okay, so you can immediately guess. I mean, if you're not asked to compute anything or show your work, you can immediately go ahead and say that the maximum is achieved when theta is equal to pi over 2. Okay, and so that's yeah, so that's what I wanted to convey with this example. So notice what you be very mindful of the variables that you choose, and sometimes when you don't have to show your work and you want to save some time, if you have something like some constant times a trigonometric function, if you identify the interval, probably if you have sine or cosine, the maximum of sine and cosine is always 1. So try to see if you have a value inside that interval where you achieve that value 1. So because then the area or that function can never be bigger than when the sine or cosine is equal to 1. Okay, so that's all I wanted to convey for this example. And now, that is conveyed with this example for practical applications in your test taking. Yes, there's some, all that is left is some general recommendations for your final exam and things. I'm gonna be posting a list of things to take a look at and to keep in mind.